Hello, welcome to today's video where we are going to be continuing our look at Argand diagrams and complex numbers in general by looking at loci. Yes, that's what we're looking at. Let's get started. Before we continue though, there are some things we should probably define and remind you of before we continue. I'm hoping that you are or have come across the word locus before in GCSE, but if not, a reminder that a locus is basically a collection of points. Now that collection of points is decided by an equation or a description normally, but for the purposes of today we are going to have everything described by an equation, but that's a general definition of what a locus is. And then exactly what that collection of points looks like will vary, but if you have the points all with a very similar relationship, it could end up that they end up being some sort of line or curve, or maybe even an entire shaded region. So yeah, that's what we're talking about when we talk about locus. Basically things you've already dealt with before. It's just that instead of having it defined per se as a y and x graph, that's why we're talking about locus. And then worth pointing out the word loci. I'll use that interchangeably with the word locus, but in reality it's specifically the plural word for locus. If you have several loci, that means you've got more than one locus. And lastly, I would hope that you're vaguely familiar with vectors. If you're not, well, you do have the option of at some point watching a video on this channel based on vectors. As of me recording this video, that video does not exist, but it will do in the future. But if not, oh well, because here's the only things you really do need to know about vectors. The first of all is if you're trying to find the vector that joins the points A all the way to B, worth pointing out first of all that notation there for vectors means you're starting at A, finishing at B. Then if A has position vector represented by vector A and point B has a position vector represented by vector B, then A to B would be the vector B minus A. Worth pointing out, therefore, noteworthy, that the point we start at is the one we take away, and the one we finish at is the one that you're starting with in the subtraction there. And the other thing I would hope you're aware of to do with vectors is what the magnitude of a vector is. The magnitude of a vector is basically finding the length of it, simply. And of course, magnitude is represented by modulus brackets. So there you go. So it's just the length of that particular vector. I'm also hoping you have already watched my other video on Argand diagrams and also modulus and argument in general, so that you're familiar with those terms when we're referring to a complex number. Brilliant. With all that said, let's start looking at some of the loci you need to know for Argand diagrams. The first of which is a loci, or sorry, I should say is a locus. I'll get the terminology correct eventually. The locus that basically ends up with you getting a circle. The equation that will define a locus of this format will be as follows. You'll have modulus brackets, you'll have a z, and then minus some sort of complex number, and then closing the brackets, and then that will be equal to r. Now the reason I've written it in this format is because the center of this circle will be represented by that complex number a plus bi. In other words, it'll have coordinates of a, b, if you're wanting to write it in that way. But it will also have a radius of r. Now that's noteworthy because it's worth pointing out this is not to be confused with the Cartesian equation of a circle, where we do end up having an r squared on the end of that format. But here, the number you see on the end equal to is just straight up the radius. No need to square root it or anything like that. You have the radius just immediately there for you to be able to use. Worth pointing out though, or trying to understand, why does this result in a circle, because that can sometimes help students remember this off by heart, because there's a very logical reason we do have this as the shape. First of all, pointing out that if you have the point A plus BI, that will be a fixed point because it will be given particular numbers for the A and the B, then you know where that is on your diagram. But then the point Z is unknown. It's a collection of points that are varying. So we could have point Z anywhere. The crucial point, though, is if we're doing Z minus A plus BI, by vectors, that means we're talking about the vector that starts at A plus BI and finishes at Z. Then if we're taking the modulus of it, we're talking about the length of this line I've just drawn. And then we're saying that length always has to have a fixed value of R. Now the thing is, if we're talking about a fixed point AB and then varying the endpoint, but always making sure that endpoint is a fixed distance away from that center, well, that's why we have a terribly drawn circle, but that's why we have a circular shape, because that's what a circle is, a collection of points that are a distance of the radius away from the center. So there you go. Right then, so doing some examples of drawing that, so therefore you get to see some more terribly drawn circles. First of all, example 1, modulus of Z minus 1 plus 3i is equal to 2. So crucial things to point out, we're taking away all of this as a complex number, so therefore the center is just the complex number 1 plus 3i. So therefore we're going to have a center, let's say 1 here, 3, let's say that's there, and then we've also got a radius of 2. So when drawing it, it's important you're not having to get out a ruler and measure a scale on the axis, so you don't want to be marking on 1, 2, 3, 4, 5, 6 on all the axes. Oh, by the way, I really should have done this, labeled my axes. But it is worth pointing out that something you do have to do is make sure that the graph makes sense. And by that I mean, for instance, we can see the center is at a height of 3, but the radius is 2. So that means we know the edge of the circle is going to be stopping before it hits the real axis. But when it comes to the imaginary axis, the vertical axis, because the center is only at 1 and the radius is 2, 2 is bigger than 1, so we're horizontally going to be traveling far enough across that we are going to be intersecting with the imaginary axis. So therefore our circle, if we draw it, should look something like this. Right, there you go. So clearly, as I showed, it's not intersecting the real axis, but it is intersecting the imaginary axis. Now, you don't have to find points of intersection per se, because they'll often be horrible numbers, but something that is a really good idea to do is to illustrate in your diagram to show what the size of the radius is. So one way you can do that is you can indicate that by doing a dotted line maybe, and then showing on the axes where the edge of the most extreme edges of the circle are at. So therefore, as it's a radius of 2, the right hand side of the circle is at 3, and the left hand side of the circle is at -1, because 1 take away 2 is -1. You could do the same for the vertical axis, so it's got a center at 3, the top will be at 5 therefore, and the bottom will be at 1. And again, you can do dotted lines if you want to show that. Or don't even bother doing the dotted lines, actually, because it can sometimes make it look a bit messy if you don't do it well. So just, put the numbers on the axes at those key important points. A second example, though. So in our first example, you might have noticed the complex number inside the modulus brackets was in brackets. That was important because it meant when we were taking it away, we knew we were taking it all away, which, as we said before, was therefore giving you the center. But as this complex number isn't in brackets with a minus in front, the way you've got to view it is basically the individual components. You can see that the real and the imaginary component, the real being 5, the imaginary being -4i, is -1 lots of whatever you can see there inside the brackets. So although it says +5, the center will be at -1 times +5, so -5. And although it says -4i inside the modulus brackets, it will be a minus, in other words, a +4i for the center of this second circle. So marking on that in the Argand diagram, let's say -5 would be somewhere over here, and then +4i would be somewhere up there, so therefore I'll be marking that over there. Cool. And then we've also, of course, got a radius, sorry, by the way, I forgot to say the other one had a radius of 2. Anyway, this one has a radius of 4. So when we come to draw this one, that's interesting because it means that because the center is 4 away from the real axis, And as we got a radius of 4, that means the edge of the circle will perfectly brush past the real axis at that point that we have marked on of -5. In other words, the real axis will be a tangent to the circle if we're using posh terminology. It's worth pointing out, therefore, you would be expected in the exam to spot that relationship, and therefore your diagram should be drawn with that in mind so that it's showing that relationship. So therefore my circle should look something very vaguely, being careful to draw it like that. Again, a dreadful circle. Your circle just needs to be good enough that the examiner can tell it's a circle, but you don't need to be bringing a compass and stuff like that into a Maths A-level or further Maths A-level exam. So, there you go. I've marked on where the centre is. It's clear where the bottom of the circle is. You could mark on, if I'd drawn my imaginary axis high enough, that the, let's extend it, there you go, that the top would therefore be at 8. And then the sides of the circle, well, they're going to start at -9 and finish at -1. There you go. So that's a good way of being able to draw these particular loci. On to the next set of loci, which is a loci that forms what we call a half line. Called a half line because normally if we have a line, it extends in both directions forever in whatever angle or gradient we should say that it is going to be at. Now, if we're talking about half lines, what format will they look like for the equation? They will be an equation of the form arg of z minus, again, a plus bi, and then that's going to equal theta. So, what will that look like? Well, it's going to be a line, half line as I said, starting at the point a plus bi. That's important because, again, you'll notice it's a minus one lot of a plus bi inside the arg notation, but then it's positive for that complex number as when we're talking about the actual point it starts at. The best way to view this is kind of similar to x direction transformations with Cartesian graphs. There is a video on that on this channel already. Go and have a look at that. But then also the line will be at an angle in comparison to the positive real axis. Let's write that down. In comparison to the positive real axis. Really, I should have typed that and had that come up as text on the video rather than terribly handwriting it. But there you go. There's the key notes from that. Why does that work? Why does it look like that? Well, again, if we're doing z, take away a minus bi, that means we're starting at a minus bi and then finishing at a point z. So we could write that. And then we're saying that makes an angle of theta with the positive real axis. And positive real axis would be, of course, a horizontal line going to the right. Now, that's all well and good if the a plus bi is lies on the positive real axis. If your real axis is below or above where our line is, so where our a plus bi is, sorry, I should say, then what you're going to have to do instead is you're going to have to, after you've drawn your line, is you're going to have to do a dotted line to simulate what the positive real axis is doing, and then you can have a reference point to mark your angle on with reference to. Sorry, I'm recording this one late in the evening, so words start to fail me. Anyway, cool. Let's start putting that into practice, though. Last thing, oh yeah, I should mention is also, of course, because we're dealing with arguments, arguments are always measured in radians. A reminder about that. So, a couple of examples. First example, we have arg of z equals minus 6 pi over 7. First thing to mention is some of you that we didn't look at the previous examples, some of you might be freaked out on this one because you go, oh my goodness, there is no takeaway inside the brackets. Where does it start therefore? Well, you could view that therefore as it being secretly z minus 0. So in other words, this particular loci is going to be starting at what would have been the origin if we're looking at these as Cartesian Cartesian pair of axes. But it's not, so therefore it's just a complex number 0, or the number 0. So, therefore our line's going to be starting there, and then it's going to be going on forever, but in the direction so that it makes an angle of minus 6 pi over 7 with the positive real axis. Now, a reminder, a minus argument means it's going anti-clockwise. So therefore, if we start at the positive real axis and then go along there, then our line might look something like, let's say, let's make it look like that. There you go. There we go. And it would just continue on forever. I've made it stop arguably a bit too early there, but key point is you would then mark on that angle there is 6 pi over 7. Don't need to mark on the minus because the fact it's minus is already clear from the fact that it's going clockwise rather than anti-clockwise. Cool. So that's the first one done. Nice. So on to a second example. So our second example looks a bit more complicated. Again, we've got a complex number inside the brackets like we did with those circle examples we were doing earlier. And therefore, watch out, because it means the line is starting at minus 2, minus 5i. So minus 2, minus 5i might be somewhere roughly over there. Again, good idea to then mark that on your axes, like so. Oops. There you go. And then we want it to have an angle of pi over 4. Now this time, because our line isn't starting on the positive real axis, therefore it's a good idea to do a dotted line going to the right, so then you have something to mark your line's angle in with reference to. So again, I'm putting that there, and then we're going to make that have an angle of pi over 4, which is, of course, 45 degrees equivalent. So there you go. That was drawn with a ruler. You probably can't believe it because that has ended up a bit bad. But anyway, roughly straight line, and therefore we can mark on that is pi over 4. However, something worth pointing out as well is, again, little things that they expect you to notice. Because pi over 4 is a very nice angle, you might remember that pi over 4, 45 degrees, is the same as saying a gradient of 1. And a reminder, if something's got a gradient of 1, that means every time it goes 1 to the right, it goes 1 up. And then the opposite is true for negative. Gradient of negative 1, every time you go 1 to the right, it goes 1 down. So the reason that's important, because it means that because we know it's starting at minus 2, minus 5, by the time it gets to the the imaginary axis, the vertical axis, it's gone 2 to the right, so therefore it must have gone 2 to the up. And therefore we know that its y-intercept, to use old language, in reality imaginary axis intercept, the intercept would be at minus 3. Cool. And you would be therefore expected to spot that that's going to happen just because it is such a nice angle. Obviously, in the previous one we had minus 6 pi over 7. If you had an angle like that, you wouldn't be expected to know where that's going to intersect because it's going to be a really horrible number. But this one was a nice number, so you'd be expected to know that. And then continue that on, you therefore also know that this real axis intercept would be 3. Again, because it's gradient of 1, by the time it's gone 3 up, it's gone 3 to the right. So that's something to be aware of. Right, okay, on to the third type of loci that you're expected to know. Right, and we're back. You could probably hear I was starting to lose my voice just then, so I had to pause. But the voice is back, so we can continue on to the third type of loci that you need to know, which is a perpendicular bisector. And the sort of equation that will lead to that is modulus of z minus a plus bi, a complex number. Close the modulus, and then, controversially, to make this different from the circle one, we're going to have another modulus on the other side, and then a different complex number, c plus di. So what this will form is a straight line that's a perpendicular bisector between the 2 points a plus bi and c plus di. So it's a perpendicular bisector in between a plus bi and c plus di. Of course, a reminder from Maths A level, a perpendicular bisector, clue is partly in the name, but breaking that down for you, perpendicular means it's 90 degrees to the 2 points, and then also bisector means cut in half, so it's going through the midpoint of the 2 points. To explain why that's happening, the notation actually does explain that and give us a clue. Because we already know from before, if we have z minus abi, that's talking about if we have the point a plus bi, and then we have the point z, don't know where that is, but let's say for the moment it's there, then z minus a plus bi will be starting at a plus bi and then finishing at z. And then if we're taking the modulus of it, we're talking about the length of that line we've drawn. But then, if we're also having on the other side z minus c plus di, well, that means we're starting at c plus di, a different point, c plus di, and then going from there to z again. But it's the same point z, because it's in an equation, wherever you see z, they're all talking about that same point. So, again, we want the length of that line as well. Now, if we're saying these two things are equal to each other, we're therefore saying these two lengths that I've drawn of the two arrows have got to be the same. And therefore, we can move z, the point z, to wherever we like, as long as those two distances remain the same. And that is why we then get a perpendicular bisector, because if you pick any point on this line, it's going to be equal distance from the 2 points for all points on that line. Cool. So with that said, let's have a look at a example. So a quick example would be this one here. So the first thing to point out again is usually we've got z minus and then 1 plus 4i all in brackets. So 1, positive 4i is the point we're marking on. So that's 1 plus 4i. So marking that on. Oops. My goodness, making lots of mistakes. That should be a 1, sorry. And then that should be a 4. And then we've also, for the other one, got just z plus 7. There is no I, so that means effectively it's like you've got a 0i there, but then the plus 7 means we've got it as minus 7. So the 2 points are positive 1, positive 4i, and minus 7 plus 0i effectively. So let's make that, let's say that's over here somewhere. Lovely. What you've got to do then to indicate that you're finding a perpendicular bisector, it's often a good idea to do a dotted line between your 2 points. By doing it dotted, you're making it clear that it's not part of your loci. That's why I've done dotted lines in some of the other loci in this video. It's because you're making a point that isn't actually, the things on the dotted line aren't actually the things that solve the equation, but they help us indicate properties of whatever it is we're drawing. But yeah, once you've done the dotted line, the perpendicular bisector will be a line that goes through the midpoint. Let's say the midpoint's about there. And then it's got to be perpendicular to what we've got. So let's say we're going to end up with something that looks something. This is probably going to go horrifically wrong. Let's say we're going to draw it like that. There we go. I did promise you go horrifically wrong. I wanted it to go through that point. Difficult to draw with a ruler on this tablet. Anyway, there you go. So, there we go. Perpendicular bisector. One last thing you can do is you can mark on a right angle symbol like that, because sometimes due to our drawing ability, it might not be obvious that a line is perpendicular to our dotted line. And so just to make it super obvious, signpost it to the examiner, show you know that it's meant to be a right angle even if it isn't perfectly a right angle. That little symbol solves all your worries. We could do another quick example, just to be aware of if you had example 2, being something as simple as z minus, let's say 3 equals z minus 5. It's worth pointing out in my first example, I didn't bother marking on the x-intercept or the y-intercept, and that's just because, hey, look, we'd have to do a lot of work to find that out, so it's not going to be a quick job where you're instantly meant to know where the x and y intercepts are. But if we look at example 2, well, we know the point 3 is there, we know the point 5 is there, and therefore, because our 2 points are horizontal to each other, the perpendicular bisector will be vertical, and therefore its midpoint is going to be 4 as well, so it's going to be a vertical line going through 4. That's important because therefore you are in that case expected to know where the in this case z or real axis intercept, I should have marked those on there, the real intercept is, because it's obvious. So basically what I'm trying to say is If it's a horrible line or a line where you're not just going to instantly be able to quickly tell where the x and the y intercepts are going to be, you're not expected to mark them on there. But if it's one like you had in example 2, you would be expected to show whether x or y intercept, or rather I should say real or imaginary intercepts, are going to be. Anyway, on to the last thing that you could be asked, and see, this isn't often included in textbooks and things like that, and it's just because it's the sort of thing they'll just occasionally slip into loci questions using this notation, just so you're expected to know what this notation means from other complex number stuff we looked at earlier. I do explain what this notation means in one of my other complex numbers videos. So, what will these sort of things look like? Well, if you have real of z equals a number, something of that form, well, what you're doing is you're setting in stone what the real component of your complex number is going to be. So that means it can't change. Now, as the real component of a number is where it is along the real axis, you're saying horizontally it's fixed in place. But we've therefore given no restrictions on what's happening vertically, because we haven't given any restrictions on what's happening to the imaginary part. So that will result in a vertical line going through just z equals k, where k is a real number. So, therefore, if we have an example of me doing that, we could have real of z equals 1, so therefore real component of 1 would be there, and therefore it's going to be a vertical line. So let's draw this on, let's draw that, and we'll say about there. There you go, drew it on a bit better this time. Let's redraw the 1 to make it obvious that it's 1, and there you go. That's that first loci done. Second sort of loci you can get is, as you probably can guess from the title of this slide, im of z equals k. Now what that means is, now this time, instead of setting in stone the real component, we're setting in stone the imaginary component. So that means we're fixed in place where we are vertically, but horizontally we can go wherever we like. And that will result in a horizontal line. And that will be going through the point z equals ki, where k is a real coefficient for that. So therefore, as a result, if we're given an example of that, then im of z equals -5. We just decide where our -5 is going to be. Let's say -5 is down there. And then get the ruler. So let's say we're about there. Terrible drawing incoming. About there. There we go. There you go. That didn't end up too bad, actually. There you go. I'm learning. So there you go. Those are 2 extra examples of things that could get involved in these questions. Not very often, but you're expected to understand what this notation means and therefore what impact that would look like visually. Okay, that is all the loci I wanted to show you in this video. It is worth mentioning that there are other loci we need to know, which is loci involving shading regions on the graph. That is going to be related to the things that you saw in this video. So either way, this video will have provided you with a basis for the next thing we're going to look at. And it is also worth pointing out there's some further loci on Argand diagrams that you need to know for the module FP2 in the Edexcel further math syllabus. But if you're not doing that module, then you don't need to worry about any further loci other than the loci regions we're going to be looking at in a very soon upcoming video. Cool. Bye bye.